Welcome to section 10.5. We're dealing with independent and dependent events. And so we are asking you questions like, if I draw one card, will it affect the second drawing that I do? And so this is the type of question that we're going to ask. Now take a look. Let's start with independent first. We're looking at events where the first one has no effect, and that is huge. It has absolutely no effect on the second event. And so please be aware of that. Now, one thing you'll notice, we're asking you the probability that both A and B occur. Let's go back to some of our basic math. The word and means multiply. And so kind of keep that in the back of your mind as you're going through. Anytime you see an and, it's probably a multiplication. So take a look. If I want the probability that both A and B occurs, then I'm going to take the probability of A and multiply it by the probability of B. Okay, so keep that in mind kind of as we're going through, but multiply means and. And this is one of the things we talked about just one more time. When you see the word and, probability of A times the probability of B. And I'm trying to give you some keys along the ways as to how to keep these equations separate. So please be aware, I'm not giving you any of the equations. You just need to know which one goes which. And so those keywords are what we're trying to show you. Okay, so knowing that we multiply, let's take a look. Each morning, a student in a class of 24 is randomly chosen to take attendance. What's the probability that the same student is chosen all 3 days? I'm going to call my student Bob. Okay, so I want to know what's the probability that Bob is chosen 3 days in a row. Well, he is one student out of the 24 in his class. So on day 1, he is the 1 out of 24. On day 2, I still want Bob, so I'm picking the person I want. So that's again 1 out of 24. On day 3, again I want Bob to be picked, so I again get 1 out of 24. Now in last chapter we knew that when you multiply fractions, you multiply in the top, so 1 times 1 times 1 is 1. And you multiply the bottom. 24 times 24 times 24 is 13,824. Okay, and so that is the probability that Bob gets selected, or any random one student gets selected 3 days in a row. Okay, and number 2 is a generally worded question, and so they're asking you if events A and B are independent. Independent should trigger this idea that you're going to multiply because we see and. They're giving you the probability in decimal form, so write your answer in decimal form. If I do the probability of A and B, I multiply the probability of A times the probability of B. So I take 0.3 and multiply it by 0.6, and what I get is 0.18. There's the probability both B and A will occur at the same time. Pretty easy formula to use. We're going to keep going. What happens if I spin a wheel? Now, let's just kind of talk about what the wheel looks like. Okay, there are 10 regions. So as I go to split this up, 1, 2, 3, 4, 5, not equally regions, but just go with me here. Okay, so there's 10 regions, and they're numbered 1 through 10. And this is just a visual. If you don't need this visual, that's okay with me too. What is the probability that 3 spins result in perfect squares? Well, let's talk about perfect squares. Perfect squares are the numbers that if you square root them, you get a whole number. 1, the square root of 4 is 2, and the square root of 9 is 3. So what's the probability on 3 spins? That means I need 3 probabilities. All right, so the probability of the first spin is 3 out of 10. Because I'm spinning again, and it won't matter what I got in the first one, my probability again is 3 out of 10. And on the third spin, again, my first 2 spins don't matter. My probability is 3 out of 10. So I get 27 out of 1,000, which cannot be reduced, so there's my probability. And again, because your spins do not affect what happens at the other spin, then they are considered 3 independent events, because my first spin doesn't affect my second spin, which doesn't affect my third spin. Okay? Let's go through this idea of a complement. This is probably the toughest example we'll see in this section, so just bear with me as we kind of go through, and I can explain again in class if we need. 2 out of every 500 coffee pots are defective. So what's the probability that at least one, whenever you see this at least, you should kind of start thinking about using a complement instead of actually having to add up different probabilities. Well, first start. The fact that a coffee pot is defective is the probability 2 out of 500, which is 1 out of 250. So 2 out of every 500 are defective. What's the probability then that it's not defective? Well, if 2 are defective, this is kind of an idea of a complement, 498 out of the 500 aren't defective. This also reduces to 249 out of 250. Okay, now, the probability that at least one pot in the 300 is defective is the same thing as, well, what's at least one means 1 or higher. So what's the opposite of that? Well, it's got to be 0. None of them are defective. Because we're talking about 300 coffee pots, we've got to affect how the probability works. And so what it says, and let me kind of give you this idea. If I want to know what's the probability that 300 coffee pots are defective, here's how it works. There are 300 independent coffee pots. So my first coffee pot has a probability of 1 out of 250, and that's reduced. My second coffee pot has also a probability that 1 out of 250, and this keeps going until I get to my 300th coffee pot, which also has a probability of 1 out of 250. So if I want the probability that 300 coffee pots are defective, it's really 1 out of 250 to the 300th power, because I'll have 300 of those probabilities. So if I'm looking at this complement idea, we want to know what's the probability that 300 coffee pots are not defective. So instead of using the 1 out of 250, I'm going to use the 498 out of 250. And because I'm talking about 300, I'm going to raise that to the 300th power. What you end up getting is approximately, I think it's 0.7, and I don't know rounding wise where it is. But what it's saying is, again, the probability that they're not defective is 498 to the 300th. And because I'm using a complement, I have to do 1 minus that probability. And so this is one of the toughest ones that we'll look at, but I wanted to at least kind of show you some of the uses for this. And this is actually real life what people do to kind of make sure that very few coffee pots come out defective. Okay, take a look. We're going to look at dependent events this time. And this is a slight difference, because dependent effects means that the first event affects what happens in the second event. And I'm going to show you a couple of ideas of what that looks like. I'm going to show you story problems, but I'm also going to show you kind of general looks at things. Okay, so let's start with the basic. The probability that B occurs after A occurs, which means that A affects B. Okay, so the probability that A affects B is called the, I apologize, excuse me. It is called what we call a conditional probability. And what that means is there are conditions, let's just rewrite it, probability. It just means that your probability is affected by A, and therefore is written with this probability of B, and this line means affected by A, okay? Even if they're affected, because we look at and, we now just multiply our probabilities together again. Okay, now let's screw that up. Let's take a look. The first event says, find the probability of A and B, given that B is affected by A. Again, because it says and, I'm still going to multiply. So I take the probability of A times the probability of B affected by A, and I say 0.3 times 0.6, which is 0.18. Okay, now I use the same numbers because I wanted you to see it's really the same idea. Our notation is slightly different. Okay, in the first one for number 2, we give you a table. What I want to know is how many males, how many females, how many total before we start. If I add up our number of males, we get a total number of 100 males. If I add up my number of females, I again get 100 females, which means I have a total of 200 people. And our totals are important when you're talking about probability. So given this table, how many people have blue eyes? Well, if I look at blue eyes, 35 and 9 makes 44, but there are 44 out of the total 200 people that have blue eyes. So my probability gets reduced to 11 out of 50. Now that's the basic probability that we did in section 10.3. So let's do this conditional probability, which says there's a fact. This is asking how many blue-eyed males out of just males. So we want to talk about blue-eyed males, and I'm going to write this out so that you can kind of see it, out of just the total number of males. Because we're looking at a subgroup, we're looking at a smaller sample, and that means it's been affected. So if I look at my number of blue-eyed males, I have 35 blue-eyed males out of the total 100 males that I have. This can be reduced to 7 out of 20. Okay, and if you see this affected by, what that means is we're limiting our population that we look at. So same thing for C. How many females have hazel eyes? That means I'm looking for hazel-eyed females out of the number of females. Okay, so how many are hazel-eyed? There are 41 out of the total 100 females, and this probability can't be reduced, so we leave it here. And so this is kind of the idea of a dependent. It just means that it's been affected in some way. I'm kind of condensing my sample size. Okay? Now, let's look at one that maybe resonates with us a little bit better. If I pass around my box of colored pencils, okay, there are 10 red ones, 8 pink ones, 13 green ones. There are 3 people in your group, so you and 2 other people, and you get the first to pick a pencil. What's the probability that all 3 of you will pick the pink? Okay, let's start with our pink pencils. Assuming that you are first, you have 8 pink pencils to pick from out of the total number of pencils, and we better find those first. If I look at total number of pencils, I add up 10, 8, and 13, which gets me 31 total pencils. Okay, so if I'm the first person to pick, there are 8 possible pink pencils out of the 31. Now, we are going to make an assumption that I actually picked a pink pencil. So if I pick a pink pencil and I go to the next person, they only have 7 pencils now out of 30 to pick from. And this is what we mean by dependent. My pick affects your drawing. And now you picked a pink pencil, and so Bob gets to pick a pencil now, and there are only 6 pink pencils left, assuming that we both picked pink, out of the 29 pencils left in the bin. And this is the idea of a dependent event. Bob's drawing depends on what you drew, which depends on what I drew. And so if I multiply across, I get 336. If I multiply in the bottom, 26,970. And I can reduce this to 56 over 4,495. Okay, and so this is the idea of a dependent event. And overall, truthfully, I think you guys are probably okay with this idea. Again, when we pick this, we are assuming I pick a pink, assuming you pick a pink, assuming Bob picks a pink. Okay? All right, last one. We're going to look at another idea of independent and dependent, and we're going to talk about marbles. And the way we look at independent and dependent is the idea of repetition and non-repetition. And so I want to kind of do this idea, or with replacement and without replacement. So I want to kind of look at what this means. And so we'll go through in the bottom two. All right, take a look. I randomly select 2 marbles from a bank containing 15 yellow, 10 red, and 12 blue. Okay, because I want a probability, I need a total. So how many total marbles are there? Well, if I add 15 and 10 and 12, I get 37 total marbles. Okay? What's the probability that my first pick is a yellow and then the second one is a not yellow? So here's the way I write it. Yellow and not yellow. Okay? And means I'm going to multiply my events together. So, all right, let's take a look. The probability that I pick a yellow first. Well, there are 15 yellow out of the 37 possible. Now, if I replace it, so I pick a yellow marble and then I put it back in the bag, there are now still 37 marbles available. And of those 37, how many are not yellow? Well, 10 red and 12 blue, so 22. So I look at this and I multiply across, and I end up getting 330 out of 1369. Here's my probability. Now, take a look. Did my first event affect what happened with my second pick? And the answer was there was no effect because I replaced it. So replacement, if it doesn't affect, means that my events are independent. Okay, if I put my marble back, then it means that my events are independent because my first draw of my marble doesn't affect my second draw. Let's look at the second one. If I don't replace the first marble. So same thing, if I'm starting with a yellow, I have 15 out of 37. But if I hold that yellow marble out of the bag, I now only have 36 marbles to choose from. I make the assumption that I keep the yellow marble. So there are still 22 other marbles that are not yellow in the bag. Okay, so if I look at it, I get 330 out of 1332, which reduces to 55 over 222. Now, did my first yellow draw affect my second one? This answer is yes. If you look, this was affected because the number at the bottom was changed. This is a dependent event then when I don't replace. And those are the kind of things we want you to keep in mind. What does it mean to be independent? What does it mean to be dependent? Okay, one last example. Drawing cards from a deck of 52. Well, if I have a spade, then a club. Well, there are 13 spades out of the 52. If I pick a spade and then put it back, there are still 52 cards to choose from, and 13 of them are clubs. So what I end up getting, and I'm just going to simplify for time, you end up getting a probability of 1 out of 16. Make sure that when you reduce this, you know how to get 1/16. Well, what happens if I don't replace? I first pick a spade, 13 out of 52. If I assume I pick the spade, I now only have 51 cards in the deck. But if I pick a spade, there are still 13 clubs. Okay? Again, I get a probability. I reduce that fraction to 13 out of 204. With replacement, again, means independent. Without replacing means dependent. And you'll notice again, my second denominator is different than my first, which means it got affected. All right, let's go one more harder. All right, I want a spade first. A spade is 13 out of 52. If I replace the cards, there are 52 left, and a club, there are 13. If I replace the spade and the club, there are still 52 cards. And since I replaced the spade, there are actually 13 spades still left. Once I find my fraction reduced, you should get a probability of 1 out of 64. The last one, let's do it different. I pick a spade, 13 out of 52. If I don't replace it, there are 51 cards available. And since I picked a spade in my first probability, there are still 13 clubs. Now, I've picked both a spade and a club, which now means there are only 50 cards available. And if I picked one spade already, there are now only 12 spades available to choose from. So I take my probability and I reduce it and get 13 out of 850. Okay? And again, our goal is to be able to determine when is it independent, when is it dependent. Dependent means there's an effect. Okay, there's some sort of fact. Independent means there's no effect. Let's make this an E because it's a fact. Okay, so that's the end of 10-5. Again, if you get a chance, start the homework.